So we're going to learn about percent composition in the beginning of this section, and then we're going to learn about empirical molecular formula tomorrow. So all of this is analytical chemistry, which is analyzing a compound to provide experimental proof of its composition and its chemical formula. And this is often used in development, especially for pharmaceutical, industrial, and home uses. So chemicals that you use in your house. Also, not just chemicals, food preservation, oil filled. We use chemicals every day. So all of those industries would be developing chemicals for some type of use. All right, so percent composition is the percent by mass of each element in a compound. And this is the formula: mass of an element over the mass of the compound times 100. So it's the mass of the element in that compound, not like from the periodic table. It depends on how many are in that compound. Percent composition of everything. If you have a compound and you find the percent composition of each atom, then they're going to add up to 100. And then sometimes you'll hear this called percent by mass. So percent composition, percent by mass, same thing. So the first example we're going to do is find the percent by mass of hydrogen and oxygen in water. So what's the formula of water? H2O. Okay. So the thing I always do is it's kind of like molar mass. When we find the molar mass, is go ahead and find the mass of each one. So how many hydrogens are in this compound? 2. And what's the mass of hydrogen? It's units or grams per mole. Okay. So then what would that give us for our total mass of hydrogen?
100. 2.
Okay. Grams per mole. I ran out of room, but you don't have to put the units for this. All right. Oxygen. There's how many oxygens? 1. What's its mass?
15.999.
And so we would get 15.999. And what do we get for a total? 18.015. So that is all the information we need for the whole thing. Now, if I wanted to find the percent of oxygen, then I'm going to do the mass of oxygen over the total mass. So what's the mass of oxygen in this compound?
15.9.
Over the total mass of this compound is 18.015. We multiply by 100, and what would we get? 88.81%. And you need to label it percent oxygen, okay? So I know what you're talking about. Okay, what about hydrogen?
11.19.
So we'd have 2.016 over 18.015 times 100. And we should get this if we calculate it. And they add up to 100. Now, I wouldn't suggest just taking your first answer and subtracting it from 100 because you could have made a mistake. And then you'll get both of them wrong instead of one of them wrong. Okay? Or none. All right, we have one more example. Okay, so our next example is the composition of NaHCO3. What's the name of NaHCO3?
Sodium.
Sodium what? Use your periodic table. Use your periodic table, use the back. Sodium hydrogen carbonate. Sometimes it's called sodium bicarbonate. So what's the common name of this? Sodium bicarbonate.
Baking soda.
Baking soda. Okay. So I don't want to calculate all these, so we're just going to find the percent of oxygen. We're going to modify this example by the percent of oxygen in sodium bicarbonate. Okay? But we still have to do this, don't we? Na, H, C, and O. That's what it's made of. How many NAs?
One.
One. What's the NA's mass?
22.
Okay. What about how many hydrogens?
One.
One. What's its mass? Carbon? Yeah, there's one. And lastly, oxygen.
15.9.
That's right. That's their total. So if we want the percent of oxygen, we have to do what? Put the mass of oxygen, which is?
47.97.
Okay, the mass of oxygen in that compound over the total
84.
times
100.
100. And what do we get? Do it on your calculator. Be sure to label percent oxygen. Now, do you have to write all this out every time? No. If you want to do it on your calculator, that's fine. But don't make a simple mistake because you skipped a step or something like that. Okay? Be careful if you just do it on your calculator. Okay, so we can use percent composition, which is what we learned yesterday. And if the elements in a new compound are known and the percent composition is known, then you could determine the formula. So it's kind of working backwards from what we did yesterday. You're given percent and you're going to calculate the formula. So the empirical formula is the first formula we're going to figure out. And it's actually the smallest whole number ratio of the elements in a compound. So that's your definition. The smallest whole number ratio of the elements in a compound. We're going to do an example of this. If we had C6H6, what would be the smallest whole number ratio of that? CH, because they're in a 1-to-1. So this is the empirical formula, and this is actually what we call the molecular formula. So there's the difference. If we had C9H12, that would be the molecular because it shows all of the molecules. But the empirical would be C3H4 because it's the smallest whole number ratio. Does that make sense? Okay. Okay, so these are the main steps to determine empirical formula if we're given percent or mass. So in the problem, it will give you either the mass of each element or the percent of each element. If you have the mass, then you skip to step 2, which is down here. If you're given percent, then you assume there's 100 grams of substance and convert to grams. So I'm going to give you an example. If you have 4.8% hydrogen and we had 100 grams of hydrogen, that would give us 100 grams of substance, then that would give us 4.87 grams of hydrogen. So basically, we're just changing this percent sign to grams. Okay. The next step, step 2, is to convert from mass to moles. So we know how to do that, grams to moles, okay, using the periodic table. Step 3 is to determine the lowest whole number ratio of the moles, and you do that by dividing by the smallest number. Okay. We're going to talk about the ratio because sometimes we'll get 1 to 1 to 2 of our molecules, and then that works. That's a whole number ratio, right? But every once in a while, we'll get 1, 1.5, and 2. Okay. If we get 1.5, that's the same as 3 halves, right? So it would be 1 to 3 halves to 2. Okay, so you can't have a 2 on the bottom. So how do we get rid of this 2 right here? We're going to have to multiply everything by 2. We can't have a fraction. We have to have a whole number. And if you multiply 1, for example, we have CHO, if those were our elements. If we multiply 1 by 2, we have to multiply them all by 2. If we multiply them by 2, this gives us 2, this would give us 3, and this would give us 4. So then our ratio would be C2H3O4, just as an example. So if you have, the main thing you need to take away from that is if you have a 2 on the bottom or 0.5, what are you going to do? Multiply by 2. Okay, because most of the time you're going to get a number, not a fraction. You're going to have 1.48. And you're like, well, that's 1.5. So I'm going to multiply everything by 2. Okay. What if you had this fraction? Let's do another example. And you can write this wherever on your notes. I don't know. 1.333. Okay. So if we had this 0.333 is 1/3, right? So that's the same as 1 1/3 or 4/3. So how do we get rid of that fraction? We're going to multiply it by 3. And what we do to 1, we do to all of them. And this one's going to give us 4. And this one's going to give us 12. Okay. Okay, so then our formula would be C3H4O12. Okay, so if you get a decimal of 0.33333, you're going to need to multiply by 3. And then the same thing, what if we had 2/3, and that decimal is 0.667. So you're going to also multiply anything with that by 3. Okay. Now, all other decimals you should get should be close to 1. So like 0.98, we round up. 0.02, we'd go down. All right. Okay, I think you have to change your example on this one because I think there's a typo in your notes. So it should be 40.05 grams of sulfur. And then I don't know what happened with oxygen, but do 59.95 grams of oxygen. So this is our first example of how to really do this. So what you're going to do first is convert, well, we're already in grams, right? So then we're going to convert from grams to moles. So if we have 40.05 grams of sulfur, and then we're going to go from grams of sulfur to 1 mole of sulfur. So we use the periodic table, and the mass of sulfur is 32.066 on your periodic table. And then we're going to use our calculator here and get an answer. And here's the important thing. When you get this answer, I want you to leave a bunch of decimal places. So I got... Okay, leave a lot of decimal places on this step. Okay. Then we're going to do the same thing for oxygen. And then grams of oxygen to 1 mole of oxygen. Look on the periodic table, and your mass of oxygen is 15.999. So that goes on the bottom. And I got for an answer 3.747. Okay. Now, so that's step 2, which is get to moles, right? Now we're in moles. Step 3 is divide by the smallest to get a whole number ratio. So this gives us 1. And this gives us what? 3. Okay, it gave me 3.000001. Okay, which is close enough to 3. So our empirical formula, that means there's one S and 3 O's. And this is not sulfite because it doesn't have a charge. Somebody always thinks it's sulfite, but it doesn't have a charge. So this is just sulfur trioxide. Okay, we're going to go on to the next example. Okay, is this the same problem you have? I think so. Yes. Okay.
525
Okay, you might have to change yours then, because this works if it's this numbers, and they add up to 100. So, okay, so we're gonna start now. This time we have percent right here. So what do? Well, basically we just turn this to grams, right? So we're just gonna change it to grams. 25.90 grams of nitrogen, and then we have 74.10 grams of oxygen. Now we go from grams to moles. Yep, but I don't know what I just... I don't know. Well, let me erase it. So, grams on bottom. All right, so in how many grams of nitrogen are in 1 mole of nitrogen? So you look at your periodic table, and it's 14.007. So then we would divide. And I got 1.84908. And then down here, oxygen, there's 15.999. I'm pretty sure y'all have that one memorized now because we've used it so much already. And here I got 4.631539. All right, divide by the smallest. And here you obviously get 1. And here I got 2.5. Okay, so if I get 0.5, I have to multiply everything by 2. Let me shuffle this over. Okay, so if I multiplied everything by 2, this one would be 2, this one would be 5. So our formula would be N2O5. That's our answer. Okay, now we're going to take this another step further. The empirical formula may or may not be the actual formula. The molecular formula is the actual ratio. So just like we did those examples earlier where we had C6H6 and then CH. This was the actual formula and this is the empirical. Okay? So we're going to determine the molecular formula. The molecular formula is a whole number ratio and a multiple of the empirical formula. So this one, right, we would say it's times 6 if we were going this way. It would be times 6. So you can, though, have the same empirical and molecular formula. It does happen. So here's how we do this. It's determined by comparing the molar mass of the compound to the mass of the empirical formula. And the molar mass comes from the problem. So make a note of that. It comes from the problem. So the mass, remember the empirical formula is what we figure out. Okay, and then I'll show you. For example, if we had an empirical formula of NO2, our molecular formula could be NO2, or it could be N2O4, or it could be N3O6, right? This is our empirical. It could be our molecular. This could be a molecular. This could be molecular. Okay? Well, how to determine the molecular formulas. So first, determine the mass of the empirical formula. So like on our last problem, we had N2O5. So you'd have to find the mass of that. So 2 times N plus 5 times O, like we've been doing. Then you're going to use the molecular mass from the problem. And you're going to determine how many times the molecular mass is greater than the empirical mass. So this is your equation. N equals the molar mass, again, from the problem, by the mass of the empirical formula. When you get that N, you're going to multiply it times your empirical formula to get your molecular formula. And all this will make sense once we do an example. These are long, but they're not that difficult. Here's an example. What is the molecular formula of a compound whose empirical formula is CH? A molecular mass is 26.04. So I've already given you the empirical formula. We don't have to figure it out. Okay? So we just need to figure out our N, which is our molecular mass, right here from the problem, divided by, it should be grams per mole. Okay, divided by our mass of this. So we have to calculate that. If we have 1C, and it's 12.011, and we have 1H, and it's 1.008, what do we get? 13.019. That's our empirical mass. That goes on the bottom. And you can clearly see it's just about 2. So our N is 2. Now we take that N equals 2. We take that N and we multiply it by our empirical formula. So this is our empirical formula. We're going to multiply it by 2. And what would that give us? How many C's? 2 C's and 2 H's. That is our molecular formula. Does that make sense that how you calculate that part? The thing is I'm not always going to give you empirical formula in the problem. Sometimes you have to calculate the empirical formula first and then find the molecular formula. Okay, it's just putting 2 things together. Do you have this example on your paper, I believe? Okay, so succinic acid is an acid produced by fungus. Chemical analysis indicates it's composed of 40.68% carbon, 5.08% hydrogen, and 54.34% oxygen. Succinic acid has a molar mass of 118.1 grams per mole. Determine the empirical and molecular formula. So always find the empirical formula first. I'm going to move this up. Here we go. So we start with our percents. And we're going to change them to grams. So we get 40.68 grams of carbon and 5.08 grams of hydrogen and 54.34 grams of oxygen. And so that's the first step, them in grams. The second step is to convert them to moles. So we have 12.011. We're using our periodic table, like still, and get an answer there. And remember to write lots of decimal places, 3.38689. Okay, that's probably good. All right, same thing with hydrogen. We're going to go grams of hydrogen to moles of hydrogen, 1.008 from the periodic table. And we get 5.03968. One more. 2, 3. Okay. And lastly, for oxygen, 15.999 grams of oxygen and 1 mole of oxygen from the periodic table. Now this is easy if you're using your yellow calculator, your TI calculator, because it saves all these numbers. And on my calculator, I will say it does not save it. So I have to go back and re-enter things. But you can just go up and highlight if you have the updated one. Okay. So then the next step is to divide by the smallest. So this one's the smallest, just slightly. And we divide all of them by that. This is clearly 1. This is clearly close enough to 1. It's like 1.002, that's 1. And then this one is 1.5. I gave you really hard examples so that the homework would be easy. So, okay, so now what do I do? If that's 1.5, I have to multiply everything by 2. So, let me change back to my pen. Times 2, times 2, times 2. And here I get 2, and here I'd get 3, and here I'd get 2. So my empirical formula, and you need to label it, we just figured it out, empirical equals C2H3O2. It's not acetate, it's not an ion, it doesn't have a charge. Okay, there's my empirical formula. Now I have to find my molecular formula, so I'm going to go back up to this problem. And it says the molar mass is 118.1 grams, right? So I have to find that N. N equals the molar mass over the empirical mass. I'm just making a little short abbreviation. So N equals 118.1 over grams per mole. The mass of this right here. So how do we calculate the mass of this right here? We're going to move this over. And we say there's 2 C's times 12.011. 20. Let me slide it over a little more. 24.022. And then there are 3 H's. Times 1.008. 3.024. And there are 2 O's times 15.999. If you want to do this all in your calculator on one step, that's fine. But just take your time and don't make a mistake. And I got 59.044. So that goes here. Finally, it's still grams per mole. This one, grams per mole. So what do I get? Can you see it? You get almost exactly 2. So now I take this 2, finally, that I got right here, and I multiply it by this to get my molecular formula. So that would make it C4H6O4. And then I'm going to put molecular. And that's my other answer. So, not very hard, just time consuming.